This video explains the design of reinforced concrete beam under shear. This need to determine the spacing of R10 stirrups that may be required near the face of the support. So if you have a support here of the 600 millimeter by 350 millimeter cantilever beam, so it's fixed here and it's loading here. Concrete compressive strength is given 25 megapascals. Tensile reinforcement, please note in this cantilever beam we have a tensile reinforcement at the top, unlike in the simply supported beam. So we have a tensile reinforcement at the top, AST 4 and 24. So we have 4 bars. So please note this is the 4 bars here. Fully anchored pass to the supports, and there are compression 2 bars, which is compression zone at the bottom, which is 2 and 20. Cover to R10 stirrup is 40, so we have 40 millimeters cover to the stirrups. Then we have these factor loads, that is 1.2 G dead load plus 1.5 live load is critical load combinations. We have given permanent dead load, which is uniformly distributed load 8 kilonewton per meter including beam self weight, and concentric load dead load is given 60 kilonewtons. Live load is given W 10 kilonewton UDL, and the concentric load given 10 kilonewtons, and the beam cross section is given here. Please note there are 4 reinforcement here, that is 4 and 24 bar, and 2 reinforcement. So this one, top one, is the tensile reinforcement, and this bottom one is because is a cantilever beam. Now here we did not, unlike in the first examples for the design of concrete reinforced concrete beam under shear, they have given the shear force diagram, but here we did not given the shear force diagram. So first of all we are going to calculate the loading. That equation is given in the questions, 1.2 G plus 1.5 Q. G is the dead load, Q is the live load. So we have a 1.2 G plus 1.5 Q. So UDL dead load is given 8. So 1.2 times 8 and plus 1.5 times live load 10. We have a live load 10 kilonewton per meter, give us 24.6 kilonewton meter. So that is UDL load 24.6 kilonewtons. Now for concentric load, we have a dead load of 60 kilonewtons. So 1.2 times 60 plus 1.5 times live load. Live load is given 90 kilonewtons. So 1.5 times 90 is given 207 kilonewtons. Now this distance from support to the concentric load is given, from the support to the concentric load is given 1.7 meters, and this is 0.1 meters from support to the end points. Now we need to first find the reaction forces. That is quite obvious here. We need to find reaction force here, and we have this reaction force. There is another one, axial reaction force. We are not considering it here. If I want to find this reaction force, we can take sum of the force in y direction equal to 0. Upward is positive. Reaction force RA upwards, this 24.6 times 1.8 that is going downwards, minus 207 equal to 0. Reaction force given 251.28 kilonewtons. Now we can, once we find the reaction force, we can find the shear force in the region AB. So let's say this is the region, AB. So we can find in the region AB what is the shear force equations. So the way we can do it is we can make the cut here, and where we make the cut, we have this shear force V going down. This reaction force we calculated 251.28 with reaction force calculated just now. UDL load 24.6, and we make the cut, and this distance x, we just use this x distance as this cut is vary between A and B. So we can say sum of the force in the y direction upward is positive, equilibrium conditions. V is downward, minus V. UDL load of the reaction force upward 251.28 minus this 24.6 times x, that is the UDL load, equal to 0. So the equation is given V equal to minus 24.6 x plus 251.28. Now we can also similarly find the equations between B and C to draw the shear force diagram. For that we are going to make the cut here. Where we make the cut, we have this V, and we redraw these whole things like reaction force, UDL, concentric load here. We use the equilibrium conditions. Sum of the force in the y direction upward is positive, so we have a minus V plus 251.28 minus 24.6x and minus 207 equal to 0, that is given V equal to minus 24.6x plus 44.28. Now using these two equations we are able to draw the shear force diagram. So I just redraw it here, and this is, let's say, support A, point B, and at C. So in this case we can draw the shear force diagram. Reaction force 251.28, slope 24.8, using these equations, and from here to here we can use this equation to calculate this one. So the our aim is not to show the shear force diagram. So this reaction force 251.28, using these equations here we can draw this one, and the slope is 24.6. These equations we can draw these lines. Our aim is to not show the shear force diagram, but the main purpose is to design the reinforced concrete beam under the shear. Now move on. We need to check that everywhere we have a V star less than or equal to VU maximum. Now this V star is nothing but that is coming from shear force diagram, maximum shear force, that is 251.28. so we can say that V star is equal to 251.28 kilonewton. That is shear force diagram. Now these equations, VU maximum is taken from the Australian standard. On page number 116, clause 8.2.3.3, we have an equation to calculate the maximum shear strength. In these equations we don't have any pre-stress, so PV equal to 0. FC dash is given in the questions, 25 megapascals. That FC dash is given in the questions, 25 megapascals. BV is the width of this beam, which is 350 millimeters, given in the questions. Now to calculate dV, first we need to calculate d0. Now please note, d0 we can calculate the distance from the tensile reinforcement to the bottom. So we have this because this is the cantilever beams. Otherwise in the normally we have the coming from here to downward, but this is tensile reinforcement to the top of the compression fiber. So d value is 600. This distance is 600. Let me put here this distance 600. This distance is 40, which is cover, given in the questions. 40 stirrups 40, covered 40 millimeters, and the stirrups diameter is 10, so take away 10. So we have a stirrups diameter 10, take away 24. Now this compression, this tensile reinforcement has a 24, that is given here. Tensile reinforcement has a 24, so 24 divided by 2, it gives 538 millimeters. So in that case we can calculate the effective shear depth, dV. Effective shear depth is given on page number 115. It is a maximum of 0.72d, 0.9d is written here. So based on this value we can calculate maximum 0.72 d. D is given in the questions, that is 600 millimeters. 0.9, and we calculate 538 millimeters. Maximum of 432 and 484, it gives us 484. We have a perpendicular rain fitment, so alpha v is 90, so cot alpha v equal to cot 90, cos 90 over sin 90, 0 over 1 gives 0. Now we substitute all this value in these equations, that big equations that I show it in the Australian standard on clause 116. We have FC 25 given in the questions, FC 25 megapascals given in the questions, BV also given in the questions, 350, dV we just calculated 484, cot theta v. Theta v is the angle of the crack. So if you have a beam, for example this is a beam, so theta v is nothing but when you have a crack, this is the 36 degree, that is the crack, and that is given in the standard. On page number 119 it says that theta v is taken 36 degree. So we substitute 36. Alpha v is the angle between the fitments. So if I want to say that and so if this is the reinforcement and that's the fitment, so this is the angle 90 degree, that is the alpha v, and we substitute all this value. PV equal to 0. These big equations, using the calculators we can find this in the newtons and divide by thousands, give us 1108. Now 5 is the VU times maximum, VU maximum. Now this reduction factor is given in table 2.2.2. in table 2.2.2 on page number 36, in E we have the class N fitments, but we have R fitments, so we take 0.7 reduction factors. That multiplication gives 766 kilonewtons, so that phi value is 0.7. Now we are checking 251.28, that is coming from the shear force diagram. We start, so we maximum shear force is 251.28, is less than the maximum shear force calculated 766. So beam size is okay, meaning that 600 by 350 millimeters is okay. If it is not okay, if it is greater, then we need to increase the beam size or increase the cross section, increase the capacity of this of the concrete, like FC dash value. And it also checked that concrete is not crossing. The concrete, the shear capacity is not governed by the concrete crossings. Next explanations will be taken in the next video. Thank you.